Kenny. I'll see if I can remember how you make these films. It's a long time since I've done it, and my memory's not so good these days. But I just wanted to explain to you something I was doing yesterday, playing with your numbers. It's probably not of much interest to you because it's not about predicting demand. I was just a little bit interested in whether you can make a mathematical model of the relationship between supply and demand, because I noticed with your impressive presentations of data that there are a couple of obvious conclusions you can draw. One is obviously that in areas with very low demand, the gap is at its largest, which is perhaps not surprising. There's not much demand in the area, presumably drivers don't wait around there very much, so there's not going to be as much supply. But also you divide it into quartiles. The quartiles seem to fit on quite a nice curve. It's a very high gap for very low demand, and it comes down, and then when you get to very high demand it starts to go up again. So I wondered if it's possible to make a mathematical model of the way supply varies with demand, you've taken groups there, because as you know, with data we have the same problem with the stock exchange data. Individual raw data tends to have a lot of scatter on it, so it's sometimes quite difficult to see trends in raw data. So sometimes it's easier to see trends if you take averages. So I took the data that you sent me yesterday about supply, demand and gap, and decided to do a rolling average of them. If you remember the rolling averages, so this is the average of, I first of all sorted them into the order of demand, so you get the districts with the lowest demand here and then gradually increasing demand, and then this is the average of the first, the lowest 10, 1 to 10, then 2 to 11, 3 to 12, and so on. So the average is in blocks of 10 all the way down. Did the same with the gap, and the same with the supply, and then tried to think about how supply should be related to demand. Now, ideally, in a simple supply-demand model, you'd expect the demand to rise with supply. Sorry, the supply, wrong way around, supply to rise in proportion to demand. For ideally, the supply would equal the demand and you'd satisfy all the demand. So the very simplest model you could have of the relationship between supply and demand is that supply increases proportionally to demand. So supply is some constant times demand, where ideally C would be 1, but in practice is likely to be less than 1. So if that simple model were true, then the supply-demand ratio would be a constant, equal to this C. So to see how well that fits the data, I plotted out the supply-demand ratio against demand, and it's kind of constant-ish for a large part of the time, in that it stays pretty close to about 0.9, between 0.9 and 0.8. But there are two obvious features when you look at this graph. A, the very beginning, the very low demand, it clearly is changing quite rapidly. So the supply-demand ratio is much lower than the expected value at very low demand, but it rises quite rapidly to get up to the sort of normal ratio quite quickly. That's probably what you'd expect, as I said, saying before, as you said. there's no point in drivers hanging around in areas where there's no demand. So the very low demand, it's going to be a problem with supply. But as you get reasonable demand, the supply will increase and eventually come up to the normal levels. So that's kind of expected. The other feature is that as the demand gets higher, the supply gets further away from it. It starts to tail off. So it's harder to meet the demand as the demand gets higher. Again, this is probably what you'd expect. It's easier to meet increasing demand at reasonably low levels. I suppose drivers can do more trips, or you can recruit more drivers. But as the demand gets high, there's a limit to the number of drivers you can recruit, and there's probably a limit to how many trips they can make. So it gets harder and harder to meet the demand, and the supply starts to lag behind demand a little bit. So this very simple model of the relationship between supply and demand obviously doesn't work and needs to be made a bit more sophisticated. So seeing the supply, seeing that curve, I thought it might be possible to have a more sophisticated supply-demand curve. So we start with the simple proportionality, some constant times the demand, but then add in another factor. Now this is an exponential factor which ensures that the supply is very low for very low demand, but rises quickly exponentially to meet the average level of supply for a particular demand. So this is what gives you the curvature at the beginning of the graph. And then this negative term at the end is what makes the supply drop below the demand as the demand gets higher. So it's the demand squared. So this only becomes important at very high demand, but it means that the supply is dropping off as the demand gets higher. So that was my proposal for mapping the way supply changes with demand. I actually changed it slightly when I did the calculation, only because these two constants here, A and B, turn out to be very, very small numbers indeed, and it's just fiddly just writing down very, very small numbers. So I slightly reformulated the equation to have divided by A, then divided by B, because A and B then are big numbers, and it's just easier to write them down. But it's basically the same equation as before. Obviously the constants are just the reciprocal of each other, so little a in the first equation, little a here is just 1 over big A, and little b is just 1 over big B. So you can use either, but just for practical purposes I use the other one. Looking at the data, this is the average data. I worked out that you probably fit the data reasonably if you used values of A and B corresponding to this. Originally I took a value of C of about 0.9. I think, perhaps the maximum ratio you're going to get is about 90% supply matching demand. But when I tried one or two calculations, it didn't seem to matter whether it is 0.9 or 1. So for the rest of the calculations I make C 1. So that's it. In theory you could get up to 100% supply meeting demand. So on the averages you get pretty good matching between the theoretical supply demand, the calculated supply demand curve, and the observed one. It could be improved. I didn't play around very much with these numbers, so it probably could be improved, but it's good enough as far as I can tell on what we've got. But the raw data, of course, is different because that's scattered about. So I just wondered how this sort of curve would fit the raw data, and so I tried doing a sort of calculated curve, which is the pink one, and then superimposing the raw data, not averaged, you're scattering about. And just to give you an idea, that's a sort of fit I did to get with that. Again, this is using slightly different values of, oh, this should be capital A and capital B, sorry, misprint there, those two should be the capitals. I didn't play around with them much, so again it could probably be improved, but as the data's scattering around quite a bit anyway, I don't think it's worth wasting too much time on it. So I think this is a way that I think it's possible to mathematically model the relationship between supply and demand, taking account of the sort of three components of it: the general way in which supply rises with demand, the part at the beginning where you get very low supply initially but rising quickly, and then the tail off at the end where supply starts to fall away again. Of course, I know this doesn't meet your problem of trying to predict demand, but I just thought I'd tell you about it in case it should be of any use to you. So that's my contribution for today. Hope everything's going well with you. Bye for now.